Hello viewers, welcome to the session on data structures. In continuation of my previous video on binary search tree, in this video we will see about the insert and delete operation and tree traversals in the binary search tree with examples. First, let us see the insert algorithm. This algorithm inserts a new element in a BST at appropriate location without violating the property of BST. So, while performing the insert operation, first the location where the given element can be inserted is identified. Then attach this new element as the appropriate subtree. So, the first step in the insert algorithm is create a tree node and set its data field with the element to be inserted and set its right and the left pointer to null. The next step is check if the tree is empty. That is, the element to be inserted is the first element. Then set it as the root. Else, check if the element is less than the data on the root. If true, then move to the left subtree. If false, then move to the right subtree. Repeat these steps until a leaf node is reached. Then attach the new element to the leaf node as the left or the right child appropriately. The routine for insert operation is given here. Note that the new element is always inserted at leaf node. So, we start searching the element from the root until we hit a leaf node. Then, the new element is attached as the appropriate child of the leaf node. Let me demonstrate the process of insertion with an example. Consider the element is equal to 65 to be inserted in the given BST. As a first step, create a new node with data set as 65 and left and right child pointer set to null. To find the appropriate location to insert 65, start the search from the root, that is 50 in this example, and compare 65 with 50. As 65 is greater than 50, proceed with the insertion process in the 50's right subtree. Now, as 65 is less than 70, proceed to 70's left subtree. As 65 is greater than 60, proceed to 60's right subtree. But as there is no subtree, then this is the location where 65 is to be inserted. Then attach 65 as the right child of the leaf node by making the right pointer of 60 to point to the new node 65. Thus, the insertion is completed. Next, let us see the algorithm for deletion. Deletion operation is performed to delete a particular element from the binary search tree. Deletion process is slightly complex as we have to consider the three possible cases of deletion differently. Case 1 is deletion of the node having no child, that is the leaf node. Case 2 is the deletion of the node having only one child. Case 3 is the deletion of the node having two children. Let us see these cases one by one. First, consider the case 1 where the deletion of a node having no child, that is the leaf node, is to be done. Deletion process is simple in this case. The first step is reach the node to be deleted, replace the leaf node with null, then free the allocated space. Next, consider the case 2 where the deletion of the node having only one child is to be done. The first step is to reach the node to be deleted. Replace the node with its child. Delete the child node by replacing it with null and free the allocated space. Next, consider the case 3 where deletion of a node having two children. There are two methods to perform this case of deletion. In method 1, reach the node to be deleted, replace the node with the smallest data of the right subtree, which is nothing but the in-order successor. The smallest data is found by performing the find-min operation in the right subtree. Then delete the smallest node following the procedure as in case 1 or 2 depending on the scenario. In method 2, reach the node to be deleted. Replace the node with the largest data of the left subtree, which is nothing but the in-order predecessor. The largest data is found by performing the find max operation. Then delete the largest node following the procedure as in case 1 or 2 depending on the scenario. So, for case 3 deletion, either method 1 or 2 is followed. The routine for deletion considering all three cases is given here. Observe the code. Let me demonstrate all three possible cases of deletion with an example. First, let us consider the case 1 scenario where the element 40 is to be deleted. This node is the leaf node. Hence, following the procedure for deletion in case 1 scenario, reach the node to be deleted starting from the root node. Here it is 50. Compare 40 with 50. As 40 is less than 50, move to the 50's left subtree. Now, as 40 is greater than 30, move to the 30's right subtree. By this, we reach the node to be deleted. Now, replace the node with null and free the space. Thus, the deletion is completed. Next, let us see the other example for case 2 scenario, where the node with only one child to be deleted. Consider the BST shown, and the element 70 is to be deleted, which is having only one child. Following the procedure of case 2 deletion, reach the node to be deleted starting from the root node, which is 50 here. Now compare 70 with 50. As 70 is greater than 50, move to the 50's right subtree. By this, we reach the node to be deleted. Now, replace 70 with its child 80. Delete the child node by replacing with null and free the space occupied by node 80. Next, let us consider the case 3 scenario where the node to be deleted has two children. So, consider the BST shown here. Let the element 30 is to be deleted, which has two children. Following the procedure of case 3 deletion, reach the node to be deleted starting from the root node, which is 50. Now compare 30 with 50. As 30 is less than 50, move to the 50's left subtree. By this, we reach the node to be deleted. Now find the node to be replaced with the method 1 or 2. I have followed method 1, and the in-order successor of 30 is found by applying the find-min operation in the right subtree of 30. The find-min operation returns the node 40. Now replace 30 with min node 40. Delete the min node 40. As here the min node is the leaf node, following the procedure for case 1 deletion, 40 is replaced with null and free the space occupied by 40. Thus, the deletion is completed. Next, let us see the operation of traversals on BST. As we know, there are three types of traversal. The procedure for traversal is similar to that followed in the binary tree. Hope you would have watched my video on binary tree traversal. Recollect and apply the same here. Consider the example tree shown here. By applying the in-order traversal, the node visited are in order 10, 20, 25, 30, 40, 50, 60, 70, and 80. Observe that the in-order traversal in a binary search tree yields all nodes in increasing order, that is, in the sorted order. Next, by applying the pre-order traversal in the same tree, we get the result as 50, 30, 20, 10, 25, 40, 70, 60, and 80. Next, by applying the post-order traversal in the same tree, we get the result as 10, 25, 20, 40, 30, 60, 80, 70, and 50. Note that to construct back the binary search tree, only pre-ordered result is used. Here, the binary search tree can be constructed by repeatedly applying the insert operation with the result of pre-order traversal. By this, we get the original tree. Next, let us see the advantages of binary search tree. In binary search tree, the searching becomes very efficient since we get a hint at each step about which subtree contains the desired element. And this binary search tree is considered as efficient data structure when compared to arrays and the linked list, as in the searching process it removes half the subtree at each step. The searching for an element in the binary search tree takes order of log n time. It also speeds up the insertion and deletion operation as compared to that in the array and the linked list. Next, let us see the applications of binary search tree. Binary search tree is used to express the arithmetic expressions. Next, to evaluate the arithmetic expressions. Next, for indexing the IP addresses. Next, to implement the dictionary. Then, to implement the multi-level indexing in database. Is used to implement Huffman coding algorithm, to implement searching algorithm, to implement routing table in router. Hope you are clear with the binary search tree. See you in the next video on AVL trees. Have a happy learning.